Ah, I see. So you think you got 13, but the rest are a little sketchy, I suppose. All right, so let's see what we got here. So we can look at this as the square root of 144 divided by the square root of y squared. And I'm going to assume today that all of the variables are positive, right? So the square root of y squared is just y again. What's the square root of 144? 12. So we get 12 over y. There you go. So you guys get that one? Some people got it. Good, good. Now this next one, we're supposed to simplify using exact, roots or whatever. And so let's see, that's really 6 times the square root of 2 times, 25, right? And then plus 7 times the square root of 4 times 8. And so we can say that that's 6 times the square root of 2 times the square root of 25. And plus 7 times the square root of 4 times, 8 is 4 times 2, right? Times the square root of 4 times the square root of 2, right? So, like, look at the factorizations of the numbers, and you can use this is the basic identity I keep using. The square root of a times b is the square root of a times the square root of b. Now, that's true as long as a and b are non-negative. That's certainly the case here, right? So, what's the square root of 25? 5, right? So you get 6 times 5, which is 30. 30 square root of 2 for the first term there. Square root of 4 is 2, right? So I've got 2 times 2 times 7, which is 4 times 7, which is 28. So plus 28 root 2. In other words, we've got 58 times the square root of 2. So there you go. How about this next one? How do we're supposed to multiply this out, right? So the usual distributive law, right? We got the square root of 12 squared minus 5 times the square root of 12 times the square root of 6 plus 5 times the square root of 6 times the square root of 12 minus 25 square root of 6 quantity squared. You notice something nice there? What's the nice thing there? Like this guy and this guy, the same thing, but with opposite signs. Yeah, they can't cancel out, right? So let's cancel out. And what's the square root of 12 squared? Yeah, I mean, in a sense that cancels. It leaves you with what? 12, right? So that's 12. And we still got this guy over here, minus 25 times what? What's the square root of 6 squared? Right, so that's 25 times 6, so that's 150. So we got 12 minus 150. So looks like minus 138. I think that makes sense because, well, can somebody work it out? If we just, as a double check on my work, it always bothers me to get a negative number for whatever reason. Can you guys tell me what the, if I can find my calculator. I know I've seen my calculator. I will find it. So I think if we calculate that factor there, we're going to see it's negative. I'll give you the decimal version of the right factor. We've got the square root of 12, right? And then minus 5 times the square root of 6. And that gives me, if you work to plug it in your calculator or whatever, you'll find out that this guy is about minus 8.78 approximately. So it makes sense that we've got a negative number, because this, of course, is clearly positive, right? Just saying. Okay, so this one here, then what? What we got? 8 times 7, which is what? 56, okay. Plus 8 root 3. Well, be careful. Yeah, minus 7 root 3. You wrote down the minus 7? Yeah. And then, so minus root 3 squared, right? Which is just 3, very good. So this guy is just 3. And, of course, this cancels 8 minus 7 is what? Just square root of 3, yeah. So we've got 56 minus 3, which is 53, plus the square root of 3.
So does that get rid of the square root?
No, but what happens... Right, I mean, basically we group these together. This gives us 8 minus 7 times the square root of 3. You could look at it that way, and then 8 minus 7 is 1. So, but however you want to look at that. I didn't do 15? Oh, in plain sight. Oops. Okay, so how are we going to do this one here? Make them smaller. Let's see here. I've got square root of 10 times the square root of a, and plus 8 times the square root of 9 times the square root of 10, right? Times the square root of a cubed, which a cubed I could write as, well, I mean, I can leave it as a cubed if you like. Of course, the square root of 9 is what? 3. And so we've got a common square root of 10 I could factor out, right? So we've got like square root of 10 times the square root of a plus 24, and then I've got, a to the what? A to the 3. I mean, I could rewrite this as a squared, square root of a squared times the square root of a if I wanted. I mean, that's one thing I'm thinking about doing. Then that would give me 24a root a. I think that's a pretty good answer. I would have, listen, I mean, this one, you see, simplify this expression is really open to interpretation. I could definitely see other possible, reasonable answers here, like square root of 10 times the square root of a plus 24 a to the 3 halves. I mean, that would be okay. Depends on the instructions. Some of the instructions said write the answer without using fractional exponents. Like if the instructions say do not use fractional exponents, then the last thing I wrote is not good, right? Because I used a fractional exponent. But yep. Class is strange. It's weird to feel like Wednesday's the start of the weekend, I don't know, it's very strange. I'm not used to this Monday, Wednesday class yet. It's very odd to me.
Do you not have any other classes?
No, I mean, I have a Monday, Wednesday, Friday pre-calculus. Like all I teach on Friday is pre-calculus. And then I have you guys Monday, Wednesday, and I have my other section of 101 Tuesday, Thursday. But it's like, 2 to 3:15. But I'm used to teaching. I mean, I've always had Tuesday, Thursday classes as long as I've been teaching, but I've never really had a Monday, Wednesday class before like this. This is it's interesting schedule. I'm also now in Wallace before I'm here. I was just upstairs, so if I'm a little bit late now to class, it's just because I'm setting stuff back up from over there. But I think I'll be on time, more or less. I was here a couple minutes before class, I think, today. So if not for not being able to find my thumb of attendance, we'd be good. I will find it. Okay, so the next topic, I mean, there's really, I would say there's kind of like three sort of major topics left, and they're not disjoint. I mean, the one is the idea of like rationalizing a denominator, all right? The other is solving equations involving radicals. We started doing that last time even, right? And then the third thing that I see on this sheet, which is related but a little bit different, is like calculating with complex numbers. So we should have time to do all of these today. So I think we'll pretty well wrap up this sheet today, if I had to guess. So what does it mean to rationalize the denominator? What do we mean by that? Basically, that just means, use some technique to eliminate radicals in the denominator. So radicals, that's just stuff with like square roots, pretty much. There are techniques for removing cube roots from denominators, but that is not a pre-calculus topic. Anyway, intermediate algebra topic. Excuse me. So here's the basic idea. If you've got something like, blah over the square root of 3, what you can do to get the square root of 3 out of the denominator is just multiply by like square root of 3 over square root of 3, which is 1. So it's blah, whatever that blah is, times the square root of 3 over 3. That's one thing you could do. Another example, you might have yada over like 2 plus root 3. Then what do you do? If you have this pattern, what you do is multiply by 2 minus root 3 over 2 minus root 3. Like that. And if you do, and that's again just multiplying by 1, right? But what happens then is you get whatever is upstairs. I just called it yada for the sake of discussion. 2 minus root 3. And downstairs, it sounds like Squidward. Is that SpongeBob?
Yes.
Okay.
Ever watched SpongeBob?
No, I have no choice. I have been subjected to the SpongeBob, but I get fed up with SpongeBob pretty fast. But turn that off. It's just.
Okay, so you have culture.
I have no culture. I don't know what you're talking about. I've watched both Naruto and Boruto and a good bit of Dragon Ball Z. I have tons of culture. You don't even know who Thanos is. You're not allowed to shake your head. It's here for. So for. Sorry. So 2 times 2 is 4. And then we have minus 2 square root of 3 plus 2 square root of 3 and minus root 3 squared, right? So you see the magic here? The radical terms cancel. See that? And they just leave you with, well, in this case, 4 minus 3, which is 1. So this one actually just ends up being equal to yada times 2 minus root 3, right? So that should pretty much help us to do most of these examples. There is something similar with complex numbers. So in the complex case, you might have something like 3 over 2 minus I. So if you want to rationalize the denominator in this sense, because remember, I is a notation for the square root of minus 1. So it's not as different as you might think at first glance. It's actually the same trick. So what you do is you multiply by 2 plus I over 2 plus I. And so we get 3 times 2 plus I divided by 4 plus 2I minus 2I minus I squared, which is, well, 6 plus 3I divided by 5. So essentially the same trick allows you to move an imaginary unit, from the denominator of a complex number to the numerator of a complex number. It's the same trick as the one above. We just changed the sign of the coefficient of the radical from plus to minus or from minus to plus and go from there. So now that we have these 3 ideas in mind, let's try to do the exercises. The first one's pretty easy. Exercise 18. Multiply by 3, square root of 17 over 3. So this is actually like square root of 17 divided by square root of 3, just to point out it's really the same as my first example. So you said multiply by 3? But remember, we can only multiply by 1, right? But your 1 is going to be square root of 3 over the square root of 3, right? We're multiplying by 1. We haven't changed the expression, right? I mean, we're going to change it in form, but not in value, so to speak. So, yeah, so square root of 17 times the square root of 3 over 3, which is, you know, the square root of whatever 17 times 3 is.
51.
Thank you. 51 over 3. There you go. That's exercise 18. Exercise 19. We have 8 plus the square root of 5 divided by the square root of 2 plus the square root of 5. Now this one, this one's a little different. Oh man, I have failed to anticipate a pattern. Curses. Oh well. You'll forgive me. I hope we can figure out how to do this one. I think if we multiply by like square root of 2 minus the square root of 5, that's going to do it. I mean, we'll try. I mean, I'm going to try that. If it works, it works. If it doesn't, then I'm going to be sad. Let's see here. So we've got 8 root 2 minus 8 root 5 plus root 2 root 5, or root 5 root 2, minus the square root of 5 squared. That's all the denominator. So root 2 times root 2 is root 2 squared, right? I think it's going to be okay, because we end up with root 2 squared plus root 2 root 5 minus root 2 root 5 root 2 minus root 5 squared. So all we're doing is multiplying out the products here, right? FOILing it out if you like, distributing.
About the answer? No.
It's a step in the answer. I mean, the whole thing is the answer, right? But
And then 5. So that makes 7.
2, okay, so yeah, 2, we get 7 in the denominator, these. So you got a 7th, and what happens upstairs?
The
Looks like I've got 8 root 2, right? Minus 8 root 5, plus the square root of 10, and then minus 5. So it is not, I mean, none of these things I don't think you can really collect, all divided by 7. So that to me, that would be a good answer right there. Here, let me give you one that's like complex kind of one. So, so this is a big example, 19 tilde. So we've got 3 plus I divided by 2 minus 3I. See if you can. So this right here, guys, if I rewrite this as 6/5 plus 3/5 I, this is the so-called Cartesian form. So the Cartesian form of a complex number is like a plus bi. All right. This, 3 over 2 minus I, this is not Cartesian form. So what we've done in this example that I gave over here is I've taken something which is not in Cartesian form and done this like rationalize the denominator trick in order to convert it to a complex number in Cartesian form. So how would you do, for example, 19 tilde? What would you guys do? What are you guys going to multiply by? Brianna, what did you multiply by?
The 2 minus 3i, but do the opposites of 2 plus 3i.
2 plus 3i. Yep, that is what you should do. You continue on, I bet you'll get it.
Yep.
2 plus 3i. 2 plus 3i. Now,
So I'm going to make the bottom cancel.
so upstairs we've got 6.
6 plus 9i
Plus 9i
plus 2i
plus
3i.
plus 3i squared. And downstairs we've got 4
Plus 9i.
minus 9i squared, but yeah. What's I squared equal to?
Negative 1.
-1.
I'll teach it and get 9 squared.
That's right, because I is the square root of -1, right? And so the denominator is actually 13, right? And the numerator, we've got 6 minus 3, which is 3. So I've got 3 plus 11i, and it's over 13, right? So there you go. I mean, I'm going to read it one more time. 3/13 plus I times 11/13. There you go. We put the complex number in so-called Cartesian form.
So is that Cartesian form?
Cartesian form is when we write it as like a number plus another number times I. That's Cartesian form. When you write a complex number in Cartesian form, you can easily like see where it is in the complex plane. So the complex plane is just like R2. Here's the complex plane. You draw the real axis this way, you draw the imaginary axis that way. So like the number 1 plus I is right here. That would be 1 plus I at that point right there. If I wanted to graph like -3 minus 2i, right here, -3 minus 2i. So, in other words, for the complex plane, the way it works is like a plus ib. You think of as the point a comma b. That's the. You guys already know how to plot points in the plane. If you want to plot points in the complex plane, if you put them into Cartesian form, you can just read off the x and the y coordinates. That's how it works.
Are we going to be doing this plotting the point to be on the test?
No, I don't think so. I don't think I have any problems on it, but just for your information, yeah.
Will there be any questions from like previous chapters or just 5 and 6?
Give me just a second. I will.
This is the test. That's the real question. Okay. I'm on it. Is
Like
it all just this?
the quiz was supposed to be today. Oh no, let me go back to my office and make the quiz. Let's see here.
Wait, is this all the tests are, or is it
I'm just messing with you. Let's see here.
you got my back? I knew it.
Well, I'm glad you guys reminded me that I got to make a quiz. I would have forgotten and just given everybody an A otherwise. I'm just talking nonsense. Let's see here. I mean, I knew the quiz wasn't today. I know because we're not done with the material yet, quite. Where was I? Your section 7 was what, Wednesday, right? So it's your section 4. Section 4, content. Let's see here. Test 3 is November 9th. Quiz 3 is next Wednesday. Yeah, so the 4th of November is quiz 3/review for test 3.
For next Wednesday?
Yeah, next Wednesday, so a week from now. So Monday, we're doing more of these examples, right? And then quiz 3 is,
Just on chapter 5 and 6?
test 3 is just on chapters 5 and 6. In fact, big final exam part 1 is also just covering tests 1, 2, and 3. So actually, what's likely to happen, if I had to guess, I think I'm probably going to cover. We may have time to cover chapter 7 this upcoming Monday, depending on how far we get today. So actually, we would be done with the material. I mean, we'd have covered the material which is in the course essentially, but I will not test on it in test 3 because I already promised you that. So that chapter 7 material would not be tested until like December 7th when you have final exam part 2. Right, so the chapter 7 material technically is not until until final exam part 2. That's slightly dishonest though, because I actually jumped ahead to chapter 7 and did completing the square, remember, and the quadratic equation on the last test. So we've already actually dabbled in chapter 7, but I'm not going to hit it full bore until the final exam part 2. So like on final exam part 2, I will ask you to like find complex solutions to quadratic equations. It will all come together. Like the quadratic part of the course will be completely fleshed out in the final exam part 2. I have intentionally avoided certain aspects of the quadratic up until now. And I will continue doing that on test 3.
So what is part 1?
Final exam part 1 is Wednesday. It's the Wednesday before Thanksgiving break. It's the 18th. Yep. And that is non-negotiable. You have to do it in class then. I don't give makeups.
Wait, what day?
If you miss it, I will require documentation. Like you didn't feel that well that day, you better go to the doctor and get a note.
Yeah, that's the part 1 of the final.
Well, part 2 is in December 7th. That's the official final exam time.
So I wasn't here, you may have already talked about it, but is there going to be any change in the class, like the classing, because of let me try that again, of them canceling like real class?
Oh, no, I already restructured the final so that it happens before Thanksgiving. So I don't really need to change much. I mean, I think the major difference will be, and this would probably happen anyway, if we were still meeting in person, is that we'll cover all of the material before like the last class meeting. So probably like the 30th of November and also the 2nd of December are more likely to just be like Zoom meetings where I'll answer questions you have about the material for final exam part 2. But I think in terms of formal lectures, maybe I'd have a little video then, but it probably wouldn't be. We'll be pretty much done in terms of new material by then, almost for certain. Yeah.
So you have to be there for part 1 of the test?
Yes.
Does that include part 2, since that's so much later and that's whenever, like, people start going home?
No, we will be home.
No one will be, the final exam part 2 is during the final exam day, which is December 7th. That will be done remotely.
Oh, okay.
Either I'll actually give the assignment during the Zoom meeting, or I will like announce it and just collect it during. I'll probably will give the problems at the start of the Zoom meeting, and then I require you to be like logged into the Zoom meeting. Maybe I'll put a password in the Zoom meeting, so you have to go to the Zoom meeting to get the password to open the thing, something like that. Because I need to see people taking the final exam part 2, because I'm supposed to proctor the test and such. I think that's an expectation of the university. So it should be an expectation of the university, even if it isn't. But anyway, does that make sense? I will, of course, send more announcements out about final exam part 1 and 2 when we get closer to them. But it's essentially, all I'm saying is, all I'm telling you right now is what's already in the course planner that's posted there. It's weird that I, split the final in half and made part of it before Thanksgiving, even before it was announced. It's almost like I knew it was coming.
Well, didn't we all?
Well, I guess we all did, yeah. Whoa! So I tried to stand up, but my body said no. Give me a second here. I will eventually. Let's try that again, but slower. Whew. All right. I still got boxes to move at home. I can't mess my back up yet. All right. Let's move on. When's the last day to work on my math lab?
15th.
Incorrect. They're all due December what? I think December 5th is when I have them all set to be due. Yeah. So if you want to, do those, they need to be done before then.
How many more chapters is it?
Just the 5, 6, and 7.
So it's chapter 1 through 7.
Mm-hmm.
That's it.
I think so. I mean, I could add more.
No.
Do you want me to add more?
Oh, that's fine.
I'm sure there's got to be something interesting past chapter 7. I haven't looked.
There isn't.
There's nothing there?
That's what
I
God
mean,
said.
sometimes I like to cover matrices in such a course as this. I mean, matrices are, you guys know about matrices?
I think your other class might like that. But we
Yeah, there's chapter 7 homework, like 7.1, 7.2. Oh yeah, it's not, you can't see it yet. If you email me that you want to see it, I'll make them visible now. I just forget to do it. If somebody wants it, I'll open them up. If you email me. That would be wise. Like 8 out of 10 conversations I have with students, like email me about that, is reciprocated by no email. So, but I really do mean it because I will forget. I mean,
put in all caps in my email.
I have been at that door before thinking, I need to send an email to the dean about something he just asked me. And I'm thinking about it at that door right there. And by the time I sit down in my office chair, it has already left my mind and I am on to something else. And later that night, I'll be lying in bed And all of a sudden I think, I'm supposed to send an email to the dean.
I'm the same way.
But now I'm in bed, and I'm not going to get up to send that email. Now, I did eventually send the email, but
I just put it in my phone to where like if it open it up. I'm like,
yeah. Let's see here. Here's exercise 21. So what we're now doing is we're solving equations involving radicals, all right? Oh, we did 20 before. So exercise 21, which you of course know since you've watched the videos from previous classes.
I do now. Yep.
Okay. Square root of y plus 1. From the notes that you've taken watching the videos of previous classes. Let's see here. Square root of y plus 1 minus 5 equals to 1. So actually, exercise 21 is almost the same as exercise 20, truth be told. I mean, exercise 21 is like a slightly more cluttered, if you will, version of 20. It's almost the same problem, really. Where did I put my good marker? Kiana? No? Kiana? Kiana? Wait a minute, what's your last name? Oh. No, I already gave you everything. I'm trying to hand stuff back. So how are we going to do? Sorry about that, Maya. How are we going to do this one? I think, first of all, move the 5 to the other side, right? That will give us the square root of y plus 1 equals to what? 1 plus 5, which is 6. Then, what do? Let's square the equation, right? Which gives me y plus 1 equals 36. So y equals 2. 36 minus 1, which is 35. What's that? And we should check our answer, right? Does it work? Let's try it out. The square root of 35 plus 1 minus 5 is the square root of 36 minus 5, which is what? 6 minus 5, right? Square root of 36 is 6. 6 minus 5 is 1, right? So, good news. We got it correct. All right. Let's try to solve exercise 22. There's no solution. Well, then how are we going to solve it? We can't, right? It's kind of a perverse use of our language, but indeed, the solution to this is that there is no solution. Because we have square root of anything, of stuff, has to be greater than or equal to 0. The square root for us, by definition, is a non-negative quantity. If you try to solve an equation with square root equal to a negative number, no solution. Now, there are some problems in the homework which ask you to find like both square roots of a number, and they'll ask for the principal square root and like the negative root, you know? So just basically the point is we always are, we implicitly assume our square root is the principal square root in here. All right, so because we do that, we can't have square root be negative. Let's see here. Can we solve, let's try exercise 24. Here we've got the square root of 2x plus 7 minus 2 equals to x. So something you want to do in these problems is to isolate the radical. That's like the first thing we want to try to do. Isolate the radical. Isolate the square root term. So how can we do that here? Add 2, right. And then what? We get rid of the radical by squaring both sides, right? So the square root of 2x plus 7 squared is just 2x plus 7. And on the other side, what do we get? Foil it out. X squared plus what? You got 4 plus 4x plus what? 2 times 2, right? So 4. All right. So now we're back to a quadratic equation, but it's not yet in standard form, right? So what we want to do is we want to move all the variables to one side and then see if we can factor it, right? Because if we could factor it, we can find the solution right quick. If we can't factor it, then we'll either use the completing the square idea, or we'll, use the quadratic formula if you like that. But let's see here. I've got x squared plus 2x minus what? 4 minus 7 is what? 3? Yeah, minus 3. Looks like it's going to factor. I think it's going to factor, like 3 and 1, or I need minus 1 and 3, or 1 and minus 3. Which one do I want? 1 and, well, if I put 1 and minus 3, then I think I get a minus 2x from that one. I think I need to flip the sign the other way, right? So x minus 1 and x plus 3, I think that'll do it for us, because then we get a minus x, but a plus 3x. So the cross term of 2x we recover from this factoring. And that, of course, is equal to 0, so what's that tell us? X equals to 1, or x equals to minus 3. And these right here are what I would call potential solutions. I say they're potential solutions because in this problem we did something in our math. We squared the equation, right? And we saw last time that when we square the equation, we may accidentally adjoin new solutions to the problem, which aren't actually solutions. They're so-called extraneous solutions, right? So we need to actually check both of these values by plugging them back into the equation and see which one, if any, is an actual solution. So plug in 1. What happens to that one? The square root of 2 plus 7 minus 2, which is the square root of 9, minus 2, which is 3 minus 2, which is 1. Good news. X equals to 1 is an honest to goodness solution. That's good. How about x equals to minus 3? So we got the square root of 2 times minus 3 plus 7 minus 2, which is the square root of 1 minus 2, right? Which is minus 1, right? And is minus 1 equal to minus 3? Right? So, no, nope. Doesn't work, right? Fails. So in other words, we cross out the minus 3. This one was extraneous. So x equals to 1 is the solution in this problem. In this sort of problem, I do expect you to box the solution, right? If you leave both the solution and the extraneous solution, then I'm supposed to take points off, you know. So part of this problem is figuring out which of your solutions from the quadratic actually are honest to goodness solutions. Now, so Brianna, like if we go back to example 22, we could trick ourselves into thinking there was a solution, right? Like the way to trick yourself into thinking there is a solution is to square the equation.
Well, that's what I did, and I got -3, and I was like, I don't know.
Uh-huh. So square root of x plus 7 squared minus 2 squared, right? So that's x plus 7 equals to 4. X equals to, like you said, minus 3. Now, here's the thing. If you tried square root of x plus 7 equals to 2, this equation does take that minus 3 as the solution. So what I'm trying to tell you is, like, when we square the equation, if you think about the starting point, there's other equations that would square to the same squared equation. Like this different equation squares to this, this equal to 4, right? Well, this squares to that, but this also squares to that, even though this equation has a solution, whereas this one does not. It's like whenever we square the equation, it may adjoin additional solutions. It doesn't always happen, though. Like there are other examples where we square the equation and we still just get one solution, you know? Like this one, we just got one solution, even though we squared it. Yeah. All right. Exercise 25 then. Solve square root of 7y plus 8 equal to the square root of 6y plus 12. Oh, by the way, something I forgot to tell you guys for this problem, exercise 22, but I think I also like this as another, so some people are like, you know, you believe me when I tell you that, oh, the square root can't be negative, right? But at the same time, you just feel like maybe there's another way to explain it. Here's another way you could explain it. If we think about y equals to the square root of x plus 7, what is that? That's half of a parabola, right? That's shifted 7 to the right. So we take the square root graph and we shift 7 to the, I say right, I meant left, 7 to the left. Right? So like this is 0 when x is equal to minus 7. And it does like this. Graphically, that's what y equals the square root of x plus 7 is, right? Where graphically is y equals minus 2? Yeah, it's down here. what's the intersection between these two graphs? There is no intersection, right? So that's another way we can understand. If we have an equation which has no solution, it's sometimes profitable to look at one side of the equation is the graph of one function, the other side of the equation is a graph of another function. And if those two graphs have no common point of intersection, that corresponds to the fact that there is no solution to the equation. It's like another way we could look at it. When I was a student, this explanation, just for whatever reason, sometimes would just make more sense to me. But in any event, what are we going to do here? Square the equation. And that gives us 7y plus 8 equals to 6y plus 12. And so if I, subtract 6y from both sides and subtract 8 from both sides, I get that, right? Which gives me what? Y equal to? 4. Yeah. And then, of course, we can check our answer, right? The square root of 7 times 4 plus 8 is the square root of 36, which is 6, right? On the other hand, the square root of 6 times 7, well, that's 42. 42 plus 12, that's the square root of, wait a minute, I can't do math. What is 6 times, why did I put a 7 there? What was wrong with me? Is that a 7? It's a 4. Sorry, I just wanted the 4. I wanted 42 to be in the problem. It's my bad. So anyway, yeah, square root of 36 again, which is 6. So, it works. Right. Checks. All right, so what is left for us to do here is all complex arithmetic, all right? So, guys, there's a definition that probably your textbook doesn't have, but it would be good for you to know about. If we have A plus IB, and we take what's called the complex conjugate of it, with a bar, put a bar over it like this, it's A minus IB. So this is what's called complex conjugate. Complex conjugation. So for example, like 3 plus 2i, complex conjugate is 3 minus 2i. So one of the things you might have noticed is if we have x plus iy and we multiply it by its complex conjugate, what happens? We get cancel. Yeah, it cancels. The imaginary part cancels, right? Yeah. We get x squared plus xy minus iyx minus I squared y squared, right?
Yeah, it cancels the
That part cancels. And I squared was what? You told me before.
-1.
Right. So this is actually x squared plus y squared. That's actually the distance from the origin to the point x plus iy in the complex plane squared. So like the significant of it is it's the length of the complex number squared.
So that first line, the first thing you wrote up there, that's the definition of complex, or that's the formula for the complex?
Yeah, that's the definition of complex conjugation. Yeah. And what I'm telling you is basically the trick that I've shared with you. If we write the complex number as z, that's what people typically do. If you want to bring the the trick that I've shared, or the rationalize the denominator, we can write it in terms of complex conjugation, like this. We multiply by z bar over z bar, and we get z bar over z bar. That's a summary of the trick I showed you earlier. Let me put numbers in. If I do like 1 over, 3 plus 2i, that's 3 minus 2i over, 3 plus 2i times 3 minus 2i, which is 3 minus 2i over 9 plus 4. My larger point to you is once you understand what's going on, you know what the denominator is going to work out to before you don't actually have to multiply that stuff out. You anticipate it being the real part squared plus the imaginary part squared. Like, it's totally unsurprising to me that we have a division by 13 when we went through the trick here. Because 13 is 3 squared plus 2 squared. But anyway, this is just some extra information for you. Now, so let me do some of our exercises. So exercise 26. Exercise 26. We have the square root of minus 100. We're supposed to express this using I. It says express the I, if you will. So what I would do is I'd say, okay, this is the square root of minus 1 times 100, right? And so we can say that's the square root of minus 1 times the square root of 100. But the square root of minus 1 is what? It's not 0, but it's just I. We give it's I. That's what I is. Square root of 100 is what? 10, right? So this is I times 10, which for reasons I don't entirely understand, I just like to write as 10i. 10i just feels right to me. I times 10 just feels wrong. I don't know why. It's just how I'm wired. It's a totally stylistic comment, but there you go. Exercise 27. You have 3 minus the square root of minus 12. You're supposed to express with I.
So how's it supposed to be in the rational?
I is supposed to be in the...
Like whenever you try to express whenever you have a negative 1 in, you have to put it inside the rational.
The main idea here is that we don't leave square root of minus 1 as part of the answer. We trade that for I. Where'd negative 1 go here? Well, the minus 12 is minus 1 times 12, right? So, here's a fun fact. If we have the square root of minus, alpha, this is equal to I times the square root of alpha, whatever alpha might be. That's just, that's a kind of a useful fact. That's what we just did in the previous thing, right? I could also say the square root of minus 100 is I times the square root of 100. Like that's a calculational step I like to make. The reason that that's true is because minus 100 is minus 1 times 100, right? And so we can think about it in this way if you like, but...
So it'd be 3 minus square root of all, minus square root of negative 1, and then...
Mm-hmm. And then the square root of minus 1 was I. The 12. Well, we could do more. I think in these kind of problems, they probably want you to notice that 12 is 4 times 3, right? So this is actually 3 minus I times square root of 4, square root of 3, which of course is